Okay. Again, reflection coefficient is defined. This is the voltage reflection coefficient. What about transmission coefficient? Transmission coefficient basically says that if I have an incoming wave, how much of that wave is going to be transmitted, which basically is equal to the load voltage, right? That's the voltage that's applied to the load. That's the total transmitted wave, which is equal to V plus V minus. So that will give us the transmission coefficient equal to 1 plus reflection coefficient. Okay, for voltage. For voltage, voltage relationship at a load, when given a load. Okay, but we can also define current reflection coefficient. This is the incoming current, and that's reflected current. It turned out by this expression, the current reflection coefficient is the same as voltage reflection coefficient, but the transmission coefficient is a little bit different. The current transmission coefficient is equal to 1 minus current reflection coefficient because of sign difference, right? Because of current sign difference. So this is the same, but this is not the same. Okay. All right. I'm not going to talk about this. I put this together for more or less completion. Okay. In general, wave propagation constant gamma, if you add resistance and conductance, okay, then it's a very complex formula. Okay. But if you assume lossless transmission, because there's no, so assume this line has no loss, then everything becomes very simple. Okay, this is a lossless transmission propagation equation. This is lossless characteristic impedance. Okay, so we're going to assume everything is lossless, make it easy. Okay, all right. Now, this is a SPICE simulation. Assuming this is a transmission line, the transmission line here is described with two parameters: the characteristic impedance and the length of the line. Okay, instead of others. Okay, of course from this you can find out the other parameters, right? So if I know the length of line in terms of in time, okay, propagation time is T d. Okay, if I know propagation time of this line, and if I know the characteristic impedance, and I also have to know the speed of the line, then I can find the length of the line. So instead of using the length, sometimes it's more convenient to use propagation delay. Okay, so in this case we use propagation delay. Okay, that's the first thing. Second thing is we assume this source is a step source. Okay, this is a step source. There's a 2 volt. See, there's a 2 volt step. Okay, so what we want to do is to find out the wave propagation of this. Okay, and the way to find this out is to use, first of all, we need to calculate the reflection coefficient. Okay, that should be gamma. It's not t. That's not t. Okay, so the reflection coefficient in this case, remember the reflection coefficient calculation, the formula. Okay, let me write down the formula. Okay. By the way, you should have a worksheet for this problem, and I think I give you a worksheet. I call this example 0, right? Mm-hmm. Example 0. Okay. How come I? Okay. Yeah, this is example 0. So first thing we need to do is to find out reflection coefficient, which is equal to Z load minus Z line divided by Z load plus Z line. Okay. In this case, the load is, and at the load is 1,000. Okay. The line is 60 ohm, and so 1,000 plus 60 ohm. Okay, this will give you the reflection coefficient, okay, at the load. So at the load, that's the reflection coefficient, right? And so, and this is a step function. When the step function started, it will propagate through this transmission line. It takes 10 nanoseconds to go through to the load. Once it reaches the load, it's going to reflect, okay? But when the reflection comes back to here, it's going to reflect again, because the reflection coefficient of the source is not 0, because the source is 30 ohm source, then line is a 60 ohm line, okay? So there's a reflection coefficient at the source, okay? It's 30 minus 60, 30 plus 60. It's negative 1/3, right? So that's the source reflection coefficient, okay? Right when the step function started, there's a wave that goes into this transmission line, okay? So the source impedance is 30 ohms. The line impedance is 60 ohms, okay? And this is a step function. When the step function started, it's a 5-volt step, right? It's a 5-volt step function. So when this 5-volt step function started, and I call it, I use V in 0 plus. Okay, so basically, this is t times equal to 0 minus. This is time equal to 0 plus. This is the boundary between the two. As soon as the step function started, we're going to have 5 volts here. But at this point, it's not going to be 5 volts. At this point, the source is going to see a 60 ohm. Okay, because that source is V plus. Okay, it's a forward-going wave. So it's going to see a 60 ohm. So at this point, V in 0 plus is going to be 5 volts times 60 ohm divided by 90. So it's 1/3 of the 5 volts, right? No, 2/3 of the 5 volts. So it's about 3.3 volts. 3.33 volts. So that's the voltage, that's V plus, that's going to propagate through this line. Okay? It's a step with 3.33 volts. Is that right? 10 over 3. Yeah. So this is 2/3, so it's 10 over 3, right? Okay. So that's the beginning voltage. So that voltage there is 3.3 volts. Okay. And then it takes 10 nanoseconds for this wave to reach this point. Once it reaches this point, you're going to have reflections, right? So I use this to time the instances to indicate the right when the wave hit this point and then when the wave started to reflect. Okay? So when the wave hit this point, you're going to have 3.3 volts. Okay? So this is VL 10 nanoseconds minus. Okay? That's VL 10 nanoseconds. That's 3.3 volts. But then you're going to have a reflection, right? What's the reflection coefficient? It's this number. What is that number? 0.89. That number is not correct. But probably this number is probably correct. Does anyone have a calculator? (1,000 minus 60 divided by 1,060). Say it again. Is that correct? Yes. Say it again. Oh, this is 1, close to 1. I believe it's 0.89. It should be correct. Is it correct? Yeah. So it's 0.89. Okay. So basically, of this 3.3 volts, 3.33 times 0.89 is going to be reflected. Okay. So at that point, this voltage here is going to be the sum of these two. That's going to be the next voltage. Okay. Right away, this VL 10 nanosecond plus is going to be 3.3 volts plus the reflected voltage. Okay, so there's a voltage change at that point. Okay, that's that voltage there. Okay, wait, how come this is current? Okay, let's forget about that. Okay, so that's one thing. Okay, another thing that we want to see is what is the final voltage? This is a step function, right? This is a step function. It's a 5-volt step forever. What is the final voltage across this? When time goes to infinity, what is the voltage on the transmission line? It's DC, right? Everything is DC. When everything is DC, what is the transmission line? What is this transmission line if it's DC? Do we need to consider this as a transmission line? No, right? So it's a short circuit. If it's a short circuit, what is the final voltage here? The step is 5-volt step, right? And then the source impedance is 30 ohms. The load impedance is 1,000 ohms. So the final voltage, L, when time goes to infinity, is about 5 volts, right? Very close to 5 volts. Because the voltage divided from between 1,000 and 30 ohms. Okay, so that's how we know roughly what's going on here. Okay, we don't know what's going on when the wave is going back and forth, but we know the initial voltage, we know the final voltage. Okay, so now what we need to do is to find out what's going on in between. Okay, and then to do that, we use a technique which is called the bounce diagram. Okay, and because I don't have a transparency, I need to draw the bounce diagram on the board. But you have a blank sheet. You can use. You can study. You can follow me. Okay. The bounce diagram describes the time and space relationship between the voltages. Okay, so let me see how we have a solution here. Let's see how we did this. Okay, 5 and 10. Okay, so basically, you use this bounce diagram. So this is the beginning. That's the source. That's 0 nanosecond. This is 5 nanosecond. This is 10 nanosecond. And this actually is called distance. Okay, so this is the load. This is the load end. Okay, that's the source end. All right, and then we use time. This is the time axis. Okay, let's see how much time we need. We need 80 nanoseconds, right? Okay, so basically this is what we can do. We can see this is 20, 40, 60, and 80 nanoseconds. Okay, so then what happens is when the wave is entered into circuit, it will take 10 nanoseconds to reach this point, right? That's 10 nanoseconds. Okay, And this wave is a 3.33 volts. That's this wave. Once it hit that point, it's going to cause reflection. Okay? And that reflection is 3.33 volts times 0.89. That's reflection. Okay? And when this reflection reaches this point, it's going to reflect. Okay? Again, it's going to reflect in this direction. How do we calculate this reflection? What is this reflection? What is 3.3 times 0.89? It's about 10% less, right? So it's about 3, right? This is close to 3 because 10% less of this. 10% is about 33. So this is close to 3 volts. Okay. Then it's going to reflect. What is reflection coefficient at this point? What is the source reflection coefficient? It's negative 1/3. So if 3 volts hit this point, how much is going to go back? Negative 1/3 of it, right? Which is negative 1. Okay? So negative 1 volts is going to go back, and it's going to hit that point. Then negative 0.89 is going to come back. Okay? And then negative 1/3 of that, which is 0.3 roughly, right? Is going to go this way, which is positive, because this is negative times negative. So positive 0.3 is going to go that way, and of that 0.27 is coming back, right? And that 0.27, a negative of that, negative third of that is going to be 0.09. It's going to go the other way, and then you have negative 0.07, right, roughly. So it's this times 8. So that's how the wave is going back and forth in space and time. Okay. So what if we want to find out the waveform in time? Okay. How do we find out the waveform in time? So if I want to draw a time axis, okay, this is a wave. This is 10, 20, 30, 40, 60, 80 in time. Okay, this is time. So this is the load voltage. All we need to do is to add these voltages together. Just add them. Okay? At a certain time. So before 10 nanoseconds, it's 0, right? At 10 nanoseconds, what is the total voltage here? What is the total voltage at this point? 6.33, right? 3.33 plus 6. So it goes all the way to 6.33. Okay? Until we got this point. What is the voltage here? It's negative 1 plus negative 89. So it's negative 1.89. So 6.33 minus negative 1.89, that will give us 4 something, right? 4.43. 4.43. And the time is, what's the time there? It's 30 nanoseconds. Okay. So it's 30 nanoseconds here. Okay. at 30 nanoseconds, the voltage is going to be 4.43, because this total voltage here is the sum of all the voltages, okay? But that's negative, so. And then at 50 nanoseconds, we have, you can see that 0.3 plus 0.27, so you have 0.57, okay? So at 50 nanoseconds, we're going to add 0.47 to this. That will give us 4.5, okay? Yeah. So we're going to have 5 volts here. All right. Now we reach this point at 70 nanoseconds. We're going to have a lower voltage because at 70 nanoseconds we have negative 0.17 added to it, right? So that will give us 4.83. Okay. Have you seen this anywhere on your scope? Have you seen a ripple on your scope? You seen this before? That's because of this propagation. Okay. This is called ripple or ringing. It's like ring back and forth. Okay. So if you have a scope, if you observe a square wave, if your period is very short, very long, you're going to see something like this, right? This is due to that probe impedance mismatch. Okay, if this impedance does not match your cable impedance, if your source impedance does not match your cable impedance, then you're going to see this kind of effect. Okay, you're going to see the wave going back and forth. This is called ringing. Okay, that's exactly because of that transmission line effect.